Okay, let's get going. So, one of the things we need to talk about is percentages. So, what you'll notice here is the percent, which has this percentage symbol, is what you've been seeing in all your syllabus lately. That's the same thing used in your syllabi. It means some sort of part of 100. Okay? So, another way of saying percentages would be parts per 100. Has anybody ever heard of parts per million, parts per billion? Yeah. So a lot of scientists will say that, parts per 100, because it's the same thing. It's just parts per million multiplied by a million, parts per billion multiplied by a billion. So on parts per 100 or percentage, what you do is you take a part, you divide it by the whole number, and then you multiply by 100. And so parts per 100, you multiply by 100, right? Makes your life a little easier to remember. And that is a percentage. I will caution against you using your percentage symbol on your calculator. I have actually seen, I would say that it is probably responsible for people that use it a fifth of their mistakes on exams. It's just wholesale a bad way to do things because you end up just hitting it and not really understanding what's going on. And then you multiply by 100 where you've already done it. Or vice versa. And so it just causes havoc and people destroy their grades using it. Okay? Make sure you practice with your calculators a little, by the way. Don't use your phones all the time, and then try to use a calculator on the exam. Okay? It will just kill you. Anybody have any questions about percentage so far? Okay. So what's the maximum percentage you should have if everything was defined correctly? Yeah, typically 100%, right? Yeah. Okay. Let's go on to the next. Mass. This is going to have to be anything that takes up space that can also be placed on a scale and weighed. Mass is going to be a measure of the amount of material in an object. There's actually a few other definitions. Mass can be a little hard to define because we exist in a place where mass is everywhere. So a common unit that's used to measure the mass of a substance is the gram. Notice there is a difference between weight and mass. Okay. The weight of an object is going to be determined by the pull of gravity on that object. That force actually does change depending on location. There's a very famous case of this in California because there's quite a few really good labs all along like a highway. And they'll take measurements at those different labs and try to talk about them. But California has quite a bit of magnetic field and actually has quite a bit of elevation differences. And so you can actually get like statistically different answers. Yeah. And that's true of weight in general. Okay. And so how we get mass on Earth typically is we actually weigh things and then we convert that number to grams. Okay. Then we convert that to a mass. When we're talking about Earth's surface, typically we kind of think of mass and weight having the same measured values and being similar things. There is a difference, though. For most of you, that's probably never going to be an issue. You'll just never work in such accurate measurements. But if you have to, it's very important you understand that. There's a difference, and you have to calibrate instruments to get the mass, whereas weight is just gravitational pull. So, okay. The volume is going to be a three-dimensional measure of the space that's occupied by matter. In lab, volumes are going to be routinely measured using graduated cylinders or a pipette would be the most common ones. Notice I did not say beaker. Beaker is not how you measure volume. We'll have a whole lab that you'll prove that to yourself, okay? All right. The unit that's typically used in lab is going to be the milliliter, ml. In clinical settings, these would also be the calibrated syringes are commonly used. They'll sometimes say ml, but as often they'll say cc or centimeter cubed. And those are actually the exact same unit, okay? cc, centimeter cubed, and milliliter, all the same amount, same unit, they're equalities, okay? One for each. 1 milliliter is going to equal 1 cubic centimeter, of course. 5 milliliters is actually a teaspoon. They redefined teaspoon to be 5 milliliters, by the way, so that is like an exact number. Unless you go to some countries which have historical teaspoons. In which case, density. This is going to be a comparison unit. It's also a ratio unit, is another way of saying that. And so you're going to have the substance's mass divided by its volume. So density, small d, substance mass divided by the volume. Okay. So 1 gram of water is going to have a mass of 1 milliliter. And density of water is 1 gram per milliliter. Now, the density of a substance is going to constantly change at a given temperature. We can actually use these density values as conversion values to determine either the mass or volume at a given temperature. That's actually how water is oftentimes used to determine the volume of something. One of the important things to keep in mind is this right here is actually demonstrating specific gravity. Okay, so when something is a higher density than something else, it tends to sink in it. When they're equal, they tend to bob within it. And then when it's less dense, it tends to float on top. And so, for example, helium balloons float in air because it's less dense than the surrounding air. Okay, cold air sinks, hot air rises. And that actually creates all sort of winds and convection currents and all sorts of things. Okay. So specific gravity. The liquid density is often going to be measured with respect to water, so you can figure out whether it would float or sink in water. It makes your life really easy. And so the density of water is 1 gram per milliliter at 4 degrees Celsius. Notice 4 degrees Celsius is very close to the value at like body temperature. And so it doesn't change much within this range around there. Okay. It's about 1. If you were to use 1.00, you'd be correct up to that uncertainty. Okay. You have to get pretty hot and pretty cold to get away from that. The ratio of the density of a sample to the density of water is going to be specific gravity, SPGR. Again, it's density of your sample divided by the density of water. If it's greater than 1, then your sample is going to sink. If it's 1, then it's going to basically be the same place as the water, and it will sort of have a band somewhere in the water. And if it's less than 1, then it's going to float. Okay. Now, the specific gravity, this is unitless because it's actually 2 densities that have the same units. You're dividing one into the other, so you cancel everything out. And so it doesn't actually have units anymore. Specific gravity of a liquid can be measured with a simple instrument. It's called a refractometer. Temperature. So the measure of temperature of a substance, you can use this to determine hotness and coldness. It's a bit of a circular definition. I'll give you a better one in just a second. There's often done using a thermometer. You can also use electronic temperature probes, which you probably also call thermometers, but technically are not. In the United States, we use the Fahrenheit scale. The rest of the world uses the Celsius scale. Scientists actually use a different scale. This is an absolute scale. So you'll notice that the scientist one, which is the Kelvin, does not have a degree symbol. Okay? Fahrenheit and Celsius have degree symbols. And that's because these ones are based off an arbitrary number. Celsius is based off 0 being the freezing point of water. Okay? This scale, which is Kelvin, which is an absolute scale, at 0 Kelvin, you actually have no heat energy. Okay? All the heat energy is gone. Right? Now, Kelvin is actually the SI unit for the temperatures. And what temperature actually is it is a measure of randomized kinetic energy. Okay? So think of it a bit like this. Like if I were to throw this to people, it has a vector, a direction, right? And it has speed and it has mass, right? And so that has a kinetic energy. I can easily calculate it. I can figure out where it's going. If I have 2 objects going opposite directions, their kinetic energies cancel, don't they? That's why when they hit each other, if they have equal kinetic energy, they just fall in place, right? Okay. What happens if I have millions, billions, trillions, 10 to the 23rd objects that I have to calculate? Do you want to do that? Nobody wants to do that, right? It's impossible, in fact. If you start having a planet of objects, we're talking 10 to the 23rd times 10 to the like tens numbers. Just massive. Okay. And so at that point, realistically, you just can't calculate individual kinetic energies anymore, can you? And so what you do is we group these things up into what's called heat. Okay. There isn't really coldness per se. There's heat being transferred somewhere else, or a lack of heat. And so that is randomized kinetic energy. The amount of randomized kinetic energy in any given system, place we're looking, is temperature. Okay, that's all that is. Okay, now you'll need to have an idea of how to do these unit conversions here of Fahrenheit to Celsius. Does anybody know that you're required to know this by international treaty as of 1988? Do you know when you were required to be trained in this and understand this and know this? Yeah, middle school. Just so funny, right? No, my day they actually did used to like make an attempt. And so they would teach you how to do these in middle school, but most people wouldn't remember it. And so,
I think I learned in 4th grade. I'm pretty sure.
Yeah.
Didn't remember it, but
oh yeah, yep, exactly, yeah. By the middle of middle school, you were supposed to know this and be able to do this. Yeah, and funny enough, Canada had the same treaty and did it. So that's why if you talk to a Canadian, they know both ways. Yeah. Okay. So 180 degrees Fahrenheit is what separates the freezing point and boiling point of water. That separation in degrees Celsius is 100 degrees Celsius. That's the separation between the freezing point, 0 degrees Celsius, and the boiling point of water, which is 100 degrees Celsius at sea level per se. That separation is actually the same amount of separation in Kelvin, because a single Kelvin is actually the same sort of unit as Celsius. They just took the Celsius and adjusted it down. Okay? Because we figured out what absolute zero was. No heat energy. Yeah. Okay. The big difference between Celsius and Kelvin is, remember that 0 degrees Celsius is actually 273, excuse me. Got my dyslexia going. 273 Kelvin. Okay? And 0 Kelvin is absolutely no heat energy. It's absolute zero.
So they took it from the freezing temperature of water to absolute zero.
Exactly. Yeah, because we figured out that was a thing. And before they had a degree, because they're like, we don't know what zero would be on this. So like a circle, we don't know where the end point is, right? Mm-hmm. And so we just, there's your end point from there. Yep. Okay, and notice, by the way, the freezing point in Fahrenheit. Anybody know why your car goes ding on cold days and then flashes the temperature? Freezing point, right? It's actually 2 degrees above freezing point because icing on bridges. But 32 degrees Fahrenheit is the freezing point of water. This right here is actually the calculations. So if you're going, Kelvin would equal degrees Celsius plus 273. Technically, it's 273.15, but mostly you guys don't need that 0.15. So. All right, and so if we look at the degrees Celsius versus degrees Fahrenheit, now I actually do something weird. I remember 180 degrees to 100 degrees. So I literally just put in 180 over 100 every time I do this. And don't bother remembering it the other way. Yeah. So the freezing boiling point difference in water in degrees Fahrenheit is 180. So 180 degrees Fahrenheit is the same distance covered as 100 degrees Celsius. And that's just how I remember it, and I don't know why. But these are actually the formulas if you want to remember it this way. By the time you're done with this class, you'll probably have this really memorized. Just I'll make you do it so many times. Okay. And so degrees Celsius, if you want to end up in that, you're going to take degrees Fahrenheit, you're going to subtract off 32, and then you're going to divide that by 1.8. Okay? Don't forget to do the addition subtraction first in your calculator, get an answer, and then do the division. Right? If you try to put this on all one line, you're probably going to miss one of these parentheses, and you're going to get 32 divided by 1.8. Okay? And not this answer divided by 1.8. All right. Now, degrees Fahrenheit, if you're trying to get degrees Fahrenheit, what you're going to do is you're going to take your degrees Celsius number, you're going to multiply it by 1.8, and then add 32. Okay? If you ever want to check yourself, did I have the right formula? Did I use that formula correctly? There's a really easy way to do this, and that is plug in 0 degrees Celsius, and that has to equal 32 Fahrenheit, right? So if you plug in 0 degrees Celsius in your formula and you get something else than 32, you have problems, right? You need to figure out where the issue is. Okay. And that's sort of always a how can I figure out if I'm wrong so I know which answers are right? That's always a good way to go about it, okay? Use things you know. Does the feather weigh 10 million kilograms? No. Does the star weigh 0.1 gram? No. Yep. Does the human weigh 1 gram? No. Okay. And so body temperature, the normal body temperature is going to be 98.6 Fahrenheit. This is 37 degrees Celsius. Body temperatures actually vary from person to person and change throughout the day. Actually, women tend to have a larger variable body temperature and can survive body temperatures that men would actually struggle with, which is kind of a weird thing. It's like one of the weird superpowers that women have for some reason, like color vision. Now, the human body temperature is going to rise above 40 degrees Celsius or 104 degrees Fahrenheit. If that happens, that's going to be called hyperthermia. Okay, hyper meaning greater, thermia meaning temperature, right? And at this point, this condition can actually cause convulsions, coma, or permanent brain damage. What's happening is your enzymes, your body functions best with a narrow temperature range. Narrow temperature range is usually a range somewhere in the 4 degrees Fahrenheit. Interestingly enough, camels can actually range 6 degrees Celsius. They're the mammals that can range the largest amounts. And so if you go above that, what ends up happening is your brain cells no longer function properly and stop doing the processes they're supposed to be able to do. And you start getting coma, of course, convulsions, and the permanent brain damage if it goes on long enough and high enough. Okay. This is actually why typically you'd curb people's fevers when they're running very high fevers. Keep in mind that when you're running a fever, what you're actually doing is you're hurting the bacteria or virus within you. By the same method, you're making it less efficient. Your body, just because it's much larger and has a lot more reserves, can usually handle more damage than a virus or a bacteria can. Okay. If your body temperature drops below 35 degrees Celsius, 95 degrees Fahrenheit, this is actually going to be hypothermia. I need to fix that. That is not hyperthermia. Hypothermia meaning hypo lower. Okay. This is going to cause you to feel cold. You're going to have an irregular heartbeat. It has a slow breathing rate. Having heard these symptoms, which one do you think is deadlier? Hypo or hyper? Hyper. Okay. Funny enough, you would think, and weirdly enough, if you're having people that just have minor amounts of both, then yes. But in actual practice, 5 times the number of people die from cold than heat. So
is that just an occurrence though, because more people experience hypothermia than hyperthermia?
Yes, to a degree. So in the case of hypothermia, if you're experiencing hypothermia, you're already in a lot of trouble. So it's something that our bodies can't resist quite as well. And what ends up happening is these are not super dangerous, these first ones. But if you start thinking about that, that's going to make you lazy. That's going to make you just sort of like relax and be, it's okay. I can keep freezing. In which case you don't act to fix it, right? And so eventually you'll freeze to death, and yeah, it's not good. Okay. Hyperthermia, on the other hand, your sweating mechanism to cool yourself is actually quite efficient. So as long as you have enough water and you're not at usually about 80% humidity and above, you can actually cool yourself even if you're in an oven. So that's actually been done, by the way. Somebody spent several days in an oven with a tube of water in their mouth. They had to leave the oven only because they ran out of electrolytes. They didn't have enough electrolytes. So they weakened because of food, not because they were hot. Yeah. So it's kind of an interesting side note to that. So hyperthermia should be deadlier. And if you're just talking about people actually having hyperthermia, then it is. But the conditions to do it are much more common, but humans are better at resisting it. So energy is going to be the capacity to do work or supply heat. It's stored energy is called potential energy. The energy of motion is called kinetic energy. Energy is going to take various forms. It's never created or destroyed, though. Hopefully everybody's heard that. Okay, fantastic. This is actually referred to as the law of conservation of energy. Energy is neither created nor destroyed. It simply changes form or gets redistributed. The SI unit for energy is the joule. The calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And so 1 calorie equals 4.184 joules. You may notice the back of your nutritional labels do not say small c calorie. They say large c calorie or large c AL. Okay. This is actually a kilocalorie. Okay. So your packages that you get, the new little nutritional labels, they actually say in the United States typically a unit that's 1,000 times the small c calorie. And so 1 big C calorie equals 1,000 small c calories, or 1 kilocalorie. Okay. I think most packages now actually have joules and calories put on them dual, because they've just went ahead and complied with the EU laws to make their lives easier. Heat and specific energy. So heat's going to be kinetic energy flowing from warmer body to a cooler one. Heat is a form of energy. In fact, it is the most common form of energy that you typically encounter. Every substance has the ability to absorb or lose heat as the temperature changes. As your temperature changes, that ability actually does change in most substances to some degree. Okay. The specific heat capacity or specific heat of a substance is going to be the amount of heat needed to raise the temperature of 1 gram of that substance 1 degree Celsius. Did anybody notice that definition's really familiar? Sounds like calorie, doesn't it? Yeah. So calorie was just working backward in specific heat. That's the specific heat of water. We just worked backwards to find energy. And that's because we didn't have any other ways of doing it. So the specific heat, SH, this is going to be the heat divided by the grams of that substance times the change in temperature. Metals are going to have very low specific heat values. That's why they heat up really, really fast. And water is going to have a very high specific heat. Do you guys know where the majority of the energy in any given economy around the world actually goes towards? Yeah, heating and cooling water. Yeah, it's actually a lot of the energy is typically the majority of any given economy. Yeah. So here's some different specific heats and how you can see water, and that's 1 calorie right there over gram degree Celsius. Here's the human body. We're a little bit smaller heat capacity. mostly because we're mostly water, but we have some other stuff in us, like salts, etc., and bone and flesh, I guess. But still, mostly water. Over here, we have things like gold, silver, copper. When you start looking at things that were used to like do heat sinks and move heat around, that's those things. Gold, silver, copper, right? And there you have iron and stainless steel. We use those as pans because they heat up pretty quick. Yeah. But aren't super soft and melt easily. All right, so let's talk about the states of matter. So there's states of matter in physical form in which the matter exists. The three most common states of matter are going to be solid, liquid, and gas. There are other states of matter, but it's unlike, well, you guys do encounter some of them. For example, lightning is plasma. The sun also has plasma. But you don't like go up to a lightning bolt and there's my plasma. So, hopefully not. So these are the ones you're going to actually encounter in your life. Here we have solid, the crystalline state, ice water. Here we have liquid, and that's just liquid water, of course. And then here we have gas. You can't actually see it except for the bubbling, but that's the water vapor, right? The gas water, gaseous water. Okay, so the four solids, the particles in a solid are going to be orderly arranged. They're going to be tightly packed together. They're going to move very, very slightly because they're so tightly bound. Okay, and so they do vibrate all the time and move around, but like very tightly packed balls and billiards, pool, right? You can't move them a lot. They just jiggle in place. Okay. Solids are going to have a definite shape and volume. That's why, for example, the desk is maintaining a definite shape and volume, right? Yeah, we can see that in the solids around us. The particles on a liquid are going to be much less ordered and moving more freely. Essentially, think of the solid, but you have broken about 20% of the connections, okay? And so what's going to happen is in a liquid, they can now flow, right? They can move around each other, because you've broken enough connections that not everything's trapped in place now, okay? And so your liquid's going to have a definite volume, but it's going to take the shape of its container. And you can see that from, would you mind holding up your water bottle for me? Thank you so much. You can see your water bottle flowing around in the container, right? But it doesn't like go up and poof. Like my water isn't just boom, right? Thank you so much. I appreciate that. Yeah, usually I have clear bottles, but today I was my metal one. Yeah. So the particles in a gas are going to have no orderly arrangement. They're very far apart from each other. They're moving at very, very high speeds. And so they do often collide with each other and the walls of the container. That's actually the pressure that's given off. You can actually feel it when you go like this. You're colliding them. And so you can feel the gas. The gas is going to have no definite shape or volume. It's going to expand to fill up whatever container it's in. So for this room, it's not like if we had like a gas introduced in this room, it wouldn't just sit here, right? It's going to fill the whole container, okay? Probably the easiest way for you to kind of know this, most gases are clear. There are visible ones, but hopefully you guys haven't actually encountered any of those. You can kind of think of smoke a little bit, but smoke isn't actually a gas, but it kind of gives definition to the gas a bit. The other way you can think of is if somebody farts, in the middle of a room, is everybody smelling that fart eventually? Yeah. Yeah. And that's the one you've all encountered the most, right? Also not a gas. Also not a gas.
Even when we can smell them?
Yeah. So what you'll notice is they actually fall out over the substances around them. Perfume, very obviously, right? The little droplets fall out on you. Mm-hmm. And it does evaporate slowly. Mm-hmm. And so that is true. Though a lot of people in this room may not have used perfume. So, maybe. I just know everybody farted. No choice in that one, right? Okay. Now, the accuracy and precision. You guys may laugh at me sometimes about that, but I really actually do have to use examples like know everybody's been. I used an example for a heterogeneous mixture once, which was a beach. So you have the water and sand, right? And I ended up with a third of my class that have never been to a beach and had no idea what I was talking about. What do you do? Need some example. Like, happens. So, accuracy and precision. Now, the stereotypical example of accuracy and precision actually uses a dartboard example. So you have a dartboard and it has a target in the middle, okay? Everybody okay with that so far? Oops, there we go. And so, if you're talking about accuracy, what that means is it accurately hits the actual or true value. They don't have to be tightly grouped, though. So, for example, if I was to take 3 points around the center here, if I average those together, what do I get? I get accuracy. So I get it targeting that true value, right? Or the target, right? So that would be accurate, but it would be low precision. So precision means that you're taking measurements and they all have similar values. And so they're very, very close together. Okay? Precision would be something like this. Very tightly grouped, right? Much tighter group than the previous one. Okay? But nothing to do with the target, are they? Way out there. Okay? So I can have extremely precise measurements and they're not accurate at all. Okay? I can have accurate measurements which are highly imprecise. Has anybody heard of like the wisdom of the crowd? If you just have people like randomly guess something and they don't know each other and they don't talk to each other, you actually get really good answers. And it's high accuracy, but really low precision. You'll get your way above, way belows, and everything in between, right? Yeah. Okay, you can be both as well, though. So if we just had 3 times all in that very center, boom, 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 that would be both, right? You'd be accurate and precise. Can you guys even see that? Yeah, you can. Okay. Yeah, it didn't show up too bad. So that's both accurate and precise, okay? Okay. This is actually really challenging to figure out accuracy. Precision's pretty easy to figure out usually. You just take more tests. If they're close together, precise, right? If they're far apart, not precise. Okay. Accuracy is much more challenging to figure out. That uncertainty we had talked about, technically that's actually a measure of, anybody know? And uncertainty we talked about, is that precision or accuracy? It's precision, isn't it? It's how tightly they're grouped together. You got it. Yeah. To do accuracy, we'd kind of have to know how what our actual value is, right? Something to compare to. Okay, let's talk about dosing. So health professionals are typically going to use SI units for a lot of things. Sometimes they'll use US customary units, and sometimes they just use old pharmaceutical units that have nothing to do with either of those. Okay, like the drops. And so these are actually the different SI metric equivalencies and the US equivalencies right there. And what I'd recommend is getting on and just like printing that so you have it near you whenever you're doing homework and stuff. So let's talk about reading lab reports here. The patient results are being given along with normal values, a normal range that they should be in. If the result is out of range, it's typically going to be highlighted. They're trying to communicate more effectively with you because honestly, the units are not going to make any sense unless you look them up, right? The values are going to be listed as greater than 1, but this makes the units on numbers vary widely. Most of the units will be metric. Typically, they're going to be listed as something over deciliter. Usually, this is millimole over deciliter. Okay? And so it'll be a millimole over a deciliter. Millimole is 1,000th of a mole. Deciliter is 1/10 of a liter. Another way of saying that is 100 milliliters. Okay? A mole of unit is going to be used to account the particles in the matter. The similar unit used would be for the electrolytes in your blood is going to be milliequivalent. That's how it's represented right there. Lowercase m, EQ for equivalent. Okay. The big difference there is milliequivalent. If you have like calcium 2+, that's going to count for 2. equivalents. Okay. Whereas like sodium, which is 1 plus, is only going to count 1 sodium per equivalent. Okay? It's because your charge matters a lot with your electrolytes. So in the United States, body weight is usually measured in pounds. A lot of pharmaceuticals that are actually done throughout the world, though, of course, measured in kilograms, right? Because that's what they do. So you'll often see that in the United States, we're giving a drug that was created by somebody outside of the United States. You're going to have to go through a series of conversions, actually. And so you go to pounds to kilograms and then dose per kilogram. Okay? Very common mathematical functions that needs to be done in hospitals. Typically, there's an app to do it for you, but every now and then things go wrong, and it's the nurse and doctors that get to do it. Okay? Like, it happens. So don't think that you can rest on your laurels forever, and the program can do everything for you. Calculating doses. This is just a straight up unit conversion, just like we did before, right? Notice the directions are exactly like we did over there, isn't it? Yeah. Drop units. So IV delivery of medications is often going to be measured in drops per milliliter. This is abbreviated GTT. GTT is actually the Latin gutta, which means drop. And so GTT is just a fancy way of saying drop. That's it. And it's a more standardized drop than you normally see, though this can cause issues, as we'll talk about in just a second. Drop factor can be used to determine the drip rates when a prescribed volume of medicine is required in a given period of time. You'll see this a lot with like the IV bags where it has the computer, and you put in a different drop factors depending on the person's body weight or how much of the dosing you need to give them. For example, like morphine. Drop factors do vary with the diameter of your IV tubing, and so it does happen. There's a variety of things that can happen. Number one, if you ever see a hospital machine, it should have a clipboard or some sort of clip on it that has like a list of times it's been calibrated and the work they've done, the dates they've done. If that's not being done on a regular basis and recently, you should get your nurse to deal with it. Okay? You should talk with your nurse, talk with your doctor, and that's a major problem. Very common problem, actually. Sometimes units like hospital wards don't get used for a while. They forget to do the maintenance, and then those items will be moved to a new ward when it's needed, and then it hasn't been maintained for a while. Okay? You'd be shocked about how often it's an issue, right? Now, why is that important? Well, the diameter of the IV tube changes your drop factor, okay? Kind of like you have different items in your kitchen, and some of them pour faster than others, right? Okay? And that's the exact same thing. If you have a different tube size, it's going to drop different drops. Simple as that, right? And so if it hasn't been calibrated recently and they don't actually know that drop factor, you can get plus minus like 50 to 100% the drug dosing. Okay? You can actually get very large swings if you wait long enough and they don't maintain that for long enough. Okay? The other thing that happens every now and then is manufacturers every now and then forget to tell their hospitals that they're changing the dang tubes. And so, or they change manufacturing of the tubes. They don't know they changed their tubes. And they just put them in as if it's going to be the same thing. And then, of course, it changes the drop factor, right? Yeah. So stuff like that happens. And it's only that's why they have the boards on them. And they calibrate them every time on a regular schedule. And so they'll know, hey, this is recently calibrated. We have the right drop factor. Okay? If you see that not being done, bring it to somebody's attention because it could save your life. Okay. So percents in health. Percent active ingredient. Because of the high potency of many medicines, binders are often be added to increase the size of your pill. You may wonder sometimes when you have like a 60 microgram UG pill, right? And you're like, that shouldn't be the size, like this big and huge horse pill looking thing. And the reason it is like that is because they couldn't weigh out the 60 micrograms. Okay. What they had to do is they mixed it huge batches and then they weighed out that dilution of it. Okay, and it really increased the accuracy of them being able to measure that out. Percent of an adult dose. So children weigh less, of course, than adults. Everybody probably knew that. And they're often going to be administered a percentage of an adult dose. Have anybody know with segways? Is that still something people know of? No. Have you guys ever seen those Coca-Cola machines that like mix themselves? Yeah. Okay, the guy that invented that, what he actually made the majority of his money on is actually meters that could give doses to babies. So pumps that could very accurately give doses to babies, which is a very challenging thing to do. So percent nutritional labels. Nutritional labels will list the amount of carbohydrates, protein, fat, as well as the daily percent daily value, showing the contribution of a single serving, suggested daily dietary requirement. Do note that this is actually based on like an imaginary individual, so it may not be the correct dosing for you. You can actually correct those doses if you ever need. Also, keep in mind that nutritional labels in the United States actually list the things that they put in to the product, not what the product actually is. Okay? So for things like yogurt, beer, etc., they actually are listing, not beer specifically, but yogurt, kombucha. Everybody knows kombucha, right? Okay, fermented drink. Any fermented drinks, they're really off. Like they'll list a large amount of sugar, but the majority of that sugar has actually been consumed by the yeast or bacteria. Okay. Beer has a specific cutout. Alcohols of all types have specific cutouts in those rules to allow them to list what's in them, like what's actually the end result. And that's why beers don't have just massive amounts of sugar numbers. If a beer was to list the same way as a soda, it would have more sugar than a soda. Okay? But they don't actually have that much sugar because the yeast uses the majority of that sugar. So they can still have a pretty good amount of sugar, though. All right, so let's talk about the HIV-1 virus particles. This is in this photo here, these little green ones. Very, very small, usually on the order of 0.000000120 meters in diameter. So very small, right? And so these are typically express their value using scientific notation and an appropriate numerical prefix to modify that basic unit so we can understand it a little easier. Okay. And so if we were to write this number in scientific notation, what should we get? Go ahead and make an attempt, please.
1.2 to the 10 to the 7.
Perfect. You got it. So 1.2 times 10 to the negative 7th. And keep in mind, because this is a smaller number, this should be a negative up here, right? So you always want to double check that. But that was perfect. And notice the correct number of sig figs, 1, 2, 3 sig figs. 1, 2, 3 sig figs, right? Okay, so if we were trying to write this with the correct prefix, what would we use? Well, we would use one of two different things, right? There's not a perfect one here. There's no 10 to the negative 7th prefix. And so most people would probably use nano, so it'd be a whole number, okay? But if you were to want to compare this to like bacteria sizes, you might want to use micro instead. You'll get a fraction, but it'll be comparable to bacteria sizes. You can list them all in one table, okay? And so, for example, micro would be 10 to the negative 6. Nano is a 10 to the negative 9 number, right? Okay. And so what we'll see here is it would be 0.120 would be our micrometers, okay? This is just the definition of micrometers. Okay. So 0.120 micrometers. Or we could write 120 nanometers, okay? So 120 nanometers. And again, this is just the definition of nanometers here, okay? Right. And that would actually represent that same number in prefix format, right? So we can more easily discuss it in like a table of values. Okay. Okay. This is the study guide, by the way, in case you guys are ever going like, hey, Dr. Clausen, what should we study for this chapter? Or, hey, Dr. Clausen, what should we study for the exam? This is the study guides for each chapters. You can just look at these for each chapter, and that is everything in there. Okay.
When you say everything in there, do you mean this would be a good thing to focus on for the upcoming
It
tests?
does an outline of all the major topics in the area.
So it's rather comprehensive.
Yeah.
If I could handle this, it would be a good.
It's more of a useful for things like, where did that topic come up again?
Okay.
And usually you're better off just, so the homeworks pretty comprehensively cover all the material,
Okay.
Along with the reviews. But don't forget to hit up definitions as well. Because if you can't talk it, you can't get asked questions about it.